Let's break down the solution for you now. So the very first step is make a little sketch. We know there's some kind of electric field and then there's some kind of charge, and we want to figure out the force acting on it. Next, we list all our knowns and unknowns. We're given that the electric field is 40 newtons per coulomb, Q is negative 10 coulombs, and we're just simply trying to find the force. Step 3, we write out the equation that relates our knowns and unknowns. In this case, we simply have the electric field equation, E equals F over Q, which we can rearrange as F equals E times Q by bringing it up. So that way when we substitute in step 4, we just take our charge Q of negative 10 coulombs and then our electric field of 40 newtons per coulomb, and we simply get an answer of negative 400 newtons. And in this case, it's going to be an attractive force since we have a negative answer. If it was a positive number, it would be a repulsive force. So for example, a positive source would push this charge away, a negative source would suck it in, but in this case we were given a negative charge here. So that's how we could figure out that this is a positive source, because it's a positive field there. But long story short, negative sign for an electrostatic force just means attractive versus positive would be a repulsive force. Next, let's talk about how do you visualize the electric field. So the rule of thumb is, again, you probe the space around an electric field with a positive test charge by definition. So it's like a positive hockey puck that you put in an ice rink that's full of electric fields. Next, you can determine the force vectors at various distance from the source of charge. You can test far away, you can test close, as you can see in this little animation. And then finally, you connect the lines of force, the force vectors, to determine what the overall field will look like. So in terms of some electric field rules, there are some simple rules of thumb we're going to follow to make our lives easier. Number 1, lines begin and end on charges. They extend to infinity and they never cross each other. Number 2, field lines will flow away from positive charges and towards negative charges because we're using a positive test charge. Number 3, if you have a larger source of charge, we're going to have more field lines. A higher density of lines indicates a stronger field. So visually, you can see right away how strong that field is. And then finally, if you have more than one source of charge, it'll be the vector sum of each individual field. That's a fancy word to just say that you add up the effect of each field at each point and you get a final vector. So for example, if I had a positive charge and a negative charge, this is very common. This is called an electric dipole. Then I could pick any point. So let's say I'll just pick a point halfway in between these two charges here. The positive source will push it to the right. The negative source will attract it to the right. So the field line is going to flow to the right. Now if I pick a point a little bit higher, let's say up here, the positive source will push it northeast. The negative source will attract it southeast. So the net effect is it's going to flow to the east here. And then once you connect all these lines, you get a cool visual pattern of what that electric field would look like around these multiple point charges here. So to wrap it up, we got a couple final electric field concept check questions to make sure you understand what's going on. First question, suppose an electric field points to the south, going down the page. Which way would a proton move in this electric field? Is it A, to the south? Is it B, to the north? Is it C, to the west? Or is it D, to the east? So would it be south down the page, north up the page, west to the left, or D, east to the right? Let's give you a second to see if you can figure this out.